Log on, tune in, find out. Another good idea from Cambridge.
Professor Isozaki from the University of Tsukuba in Japan, and he will give a talk on inverse scattering from cusp on generalized arithmetic.
Thank you, organizers. Also, I'm one of them to use this opportunity. It's a joint work with Hiroshi and Maki. We are working on this sort of problem for more, yeah? Oh, thank you very much. For more than 5 years, I think. And it's a great pleasure for me to give a talk for this subject before Professor Fadiev, because I admire very much about his work on three-body problem and the inverse problem, and also this paper, which showed us for the first time to use the spectral theory to hyperbolic spaces. And I'm going to talk about these subjects, basic facts from hyperbolic geometry, surfaces with cusps and conic singularities, eigenfunction expansions, and then I introduced generalized S matrix and state the result. So our mounting example is a Riemann surface with cusp. And this is a classical topic, and it's better to explain the basic facts because it is just in between algebra, geometry, and analysis. Now, you know that any hyperbolic manifolds are constructed by the action of discrete groups on the unit disk or the upper half plane. Now let us pick up the upper half space model. So consider the upper half space in two-dimensional space equipped with this metric. This makes this upper half space the hyperbolic space. And we consider the group SL2R and let G act on upper half space by this action via the fractional linear transformation. This gives you the isometry on upper half space with that metric. Now we take a discrete subgroup of SL2R called the Fuchsian group and consider the quotient space by this action. And we usually consider the geometric finite case. It means that the fundamental domain consists of a finite side convex polygon. This is equivalent to that the group gamma is finitely generated. The simplest example of the discrete group is translation, horizontal translation. Then the quotient space is just this one. You identify these two lines, then you have this sort of cylinder. However, because of the metric, this part becomes a finite measure. However, this end part has an infinite measure. So it's like the horn, and you call this top the cusp, and let us call this bottom the regular infinity. So this is the simplest example. The next simple example is a group generated by dilation. Then the fundamental domain is formed by these two half spheres, half circles. Then you again have something like this tube. And this end part is usually called a funnel. And if you take the coordinates like this, if you take the geodesic distance r, then the induced metric becomes of this form. So it means that the funnel is a small perturbation
the regular infinity for the case of the cylinder. So it means that this cusp and the regular infinity is a standard model of the infinity of the hyperbolic space. Now there is a classification theorem of a two-dimensional hypermanifold. Namely, take any two-dimensional hyperbolic manifold, and then you remove the compact part from it. Then the remaining part consists of a finite set of cusps and funnels. So this means that the most general example of the two-dimensional hypermanifold of geometrically finite class has this form. You have a finite number of cusps and a finite number of funnels. And there's an important subgroup of the Fuchsian group, which calls the Fuchsian group of the first kind. And this often appears in number theory. I don't give the definition of the group of the first kind, but anyhow, it's equivalent to that. The fundamental domain has a finite measure. It then implies that M gamma is automatically geometrically finite. And if you open the book of hyperbolic geometry, you see this sort of picture. This is a standard fundamental domain for the Fuchsian group of the first kind. Here you have the cusp, and you don't have the regular infinity because the fundamental domain has a finite measure. Now, suppose you are given a group of Fuchsian group of the first kind. Then the ends of the fundamental domain has a finite number of cusps, and usually you compactify this domain and regard it as a Riemann surface. So you now have a compact Riemann surface. Then the set of meromorphic functions on this Riemann surface forms an algebraic function field. And it's well known that there is a one-to-one correspondence between the algebraic function fields and the compact Riemann surface. What does it mean? It means that the surface is determined by a set of functions on it. What we want to consider is the generalization of this fact. And I guess the answer is this one. Instead of as a function space, we consider the solution space of the Helmholtz equation. And more precisely, we look at the behavior of solutions of the Helmholtz equation at infinity. This gives you the definition of S matrix. Now, let us recall our example of the geometrically finite hyperbolic space. So you have funnels here, the cusp here, and also you have some singular points here. There is another classification of the hyperbolic space, of points in the hyperbolic space, by the action of the discrete group. The matrix gamma is said to be hyperbolic if you have two fixed points on the boundary, two different fixed points on the boundary. It's called hyperbolic. If these 2 points degenerate to one point, it's called parabolic. And if you have one fixed point in the upper half plane and the one point in the lower half plane, it's called elliptic. And let M thing be the set of elliptic fixed points, and let IP be the isotropy group which fixes this fixed point. Then, Okay, originally this hyperbolic plane was equipped with hyperbolic geometry, hyperbolic distance. Now, so this makes this M gamma as a hyperbolic space, and by introducing suitable local coordinates, this P, singular point P, around this singular point P, you can introduce an analytic local coordinate. So the manifold itself is a smooth manifold without singularity. However, if you induce the metric, hyperbolic metric, this metric becomes singular at this singular point. And around this singular point, this quotient space has a special structure. By a suitable choice of local coordinates around this singular point, the isotropy group turns out to be a finite group of rotations. And then you can take a neighborhood of P, which is like a sector with vertex at P. For example, in the case of SL to Z over H2, the fundamental domain is like this. So this is a singular point, and around the singular point, the fundamental domain becomes like a sector. And in this case, the rotation group is a rotation group of order 3. So this M gamma admits a covering space, which is actually this one. And this covering space is automatically a hyperbolic space. And for us, it is much more convenient to change another change of local coordinates by which the manifold is no longer analytic. However, the metric has this form. You have a constant n squared here, and n is the order of this isotropy group. So for us, it's more convenient to introduce the notion of conical singularities on this manifold. So I give the definition of two-dimensional Riemannian surface with conical singularities. So we consider a two-dimensional connected infinity manifold, which is written as a union of open sets satisfying the following assumptions. We are mainly considering this sort of space, where you have some finite part, and you have some infinite part, this one or this one, and you have some singular points here. And we assume that there are n infinite paths, which we call ends of the manifold, and assume that the ends are classified into two parts. The first one is isometric to this space S1 times 1 infinity equipped with this metric. So this part is a cusp. This is the cusp case. And the other ends has form is diffeomorphic to S1 times 0, 0, 1, and the metric has this form, and this H is roughly, so this is it's better to HS, so let us forget this part. A dy squared plus dx squared. So this is a standard small perturbation of the regular infinity. So we have two ends. This is a cusp part, and this is a small perturbation of the regular ends. this is the ends of our manifold. And the perturbation decays like in this way. So this is a short range perturbation because log y is a geodesic distance. And we assume that there is a finite set such that except for these finite sets, the manifold is smooth. And of course, the manifold itself is smooth. However, around this special point, you have the following structure. By taking a suitable geodesic polar coordinates, the matrix has this form. It's almost like r squared plus something small, and you have constant Cp here, which is different from 1. In the case of the quotient space of the hypermanifold, Cp was just 1 over n squared, where n was the order of rotation group. And you can regard it as, you can deal with it as the usual, just like the usual smooth Riemannian manifold. You can define the Laplace-Bertrand operator and its self-adjoint extension. And by subtracting -1/4 from this Laplace-Bertrand operator, the essential spectrum is 0 infinity. It doesn't have embedded eigenvalues if you have a regular infinity. If all the ends is a cusp, it may have embedded eigenvalues. However, it is discrete. The accumulation point is only 0 or infinity. Now, to study the Schrödinger equation or Helmholtz equation on this manifold, it's better to introduce a space which leads the standard L2 over M. And this P is defined by the dyadic decomposition of the end. And what is important is the structure of this bigger space B star. So if you take this model, the most standard case of this cylinder, this space B star is 0 infinity times S1 L2 equipped with this metric, where this H is L2 S1. This H, sorry, it was not this one, L2 S1. Okay, L2 S1. We consider this space equipped with this metric, this measure. So it means that the space, the function in this B star behaves like y to the power 1/2, which is just the standard behavior of the solution to the Schrödinger equation at infinity. And we write fy is almost equal to gy. If this holds, it means that these two functions behave similarly at infinity. So they have the same behavior at infinity. Then, by observing the resolvent behavior of the resolvent at infinity, just like the far field pattern, you can define the Fourier transform on this manifold. And this for describe this Fourier transform, you need representation space, the space at infinity, and it's very simple. For the cusp case, it's just the complex plane C, and for the regular infinity, it's just L2 S1. and you consider the L space with space of L2 functions over 0 infinity. This is a spectrum, and this H is the space at infinity. And you consider the Fourier transform, which maps function over this manifold to this space. Then this is a unitary operator which diagonalizes the original Schrödinger operator. And its adjoint is very important. Its adjoint is an eigenoperator, or here you often say Hilbert's operator or Poisson operator, which maps the function of the space at infinity to the space B star. And this is an eigenoperator in the sense that this Schrödinger equation holds. And this space B star is very important because it characterizes all physical solution of the Helmholtz equation. Namely, the solution of the Helmholtz equation sitting in this space B star is written by the image of L2 functions over this manifold at infinity by this Poisson operator. So this space B star characterizes all the solution of the physical solution of the Schrödinger equation. So let us recall the well-known theorem of Helgason, which says that in the case of a Poincare disk, all the solution of the Helmholtz equation in the Poincare disk is written by Poisson integral of Sato's hyperfunction on the boundary. So instead of hyperfunction, we take L2 functions on the boundary. So this makes our space. And what is the feature of this space? This is the smallest space with respect to the decay of the solution for the Helmholtz equation. Namely, if you have a solution to the Helmholtz equation which decays faster than the elements in B star, then it must vanish identically. So it means that this is the smallest, this is the fastest decay of physical solution to the Schrödinger equation. And any solution in B star of the Helmholtz equation admits the following asymptotic expansion. Namely, in any ends, it has this form. Here you have this. This n is now equal to 2. This n is now equal to 2. And you have this factor, this amplitude term, and you have this oscillating term. And these are the functions. These Cj minus or Cj plus are the functions at infinity on this space. So this gives you the incoming wave, and this gives you the outgoing wave. And if you are going, and we have the following theorem. If you are given this incoming wave, there exists unique solution U of the Helmholtz equation which have this incoming wave and which admits this outgoing wave. And the map which assigns this incoming wave to the outgoing wave is the S matrix. Actually, this is something unitary equivalent to the standard S matrix, but let us forget it. Let us call it the S matrix. And although B star is the smallest space for the Helmholtz equation, this solution contains a sufficient knowledge to determine the whole manifold. So suppose so let us consider the case of the regular infinity. You send a wave from here, a physical wave from here, and you look at the reflected wave here. this gives you the component of the S matrix in this end. This information is sufficient to determine the whole manifold. And so there's a work of Sabarator and also the Kuldev and myself, which says that from this information, you can determine all the manifold. So it means that if one end is regular, this S matrix determines all over the manifold to recover the manifold. However, it does not cover the case of the Fuchsian group of the first kind. In that case, you don't have a regular infinity, you only have cusps. So what shall we do? Why it happens? Because the cusp gives only one-dimensional contribution to the continuous spectrum. So it does have enough knowledge to determine the whole manifold. Now, what shall we do? Let us consider the Schrödinger equation on the end. By passing to the Fourier series, each component of the Schrödinger equation satisfies this one-dimensional equation, and the solution is written by modified Hankel functions, modified Bessel functions. And by looking at the behavior of the modified Bessel functions, you see that at the cusp, all the solutions behave like of this form. So you have a term which goes exponentially, which is exponentially growing at the cusp, and also exponentially decaying at the cusp. And by looking at this part, you define the usual S matrix, physical S matrix. However, if you look at all the solutions of the Schrödinger equation, you have this outgoing, this exponentially growing part and exponentially decaying part. So we define, you define the space of generalized scattering data at infinity. It consists of the, so for the case of the cusp, it consists of an infinite series, which is L2 minus infinity is exponentially growing, and this is exponentially decaying. And if you associate a Fourier series for these coefficients, you have a analytic functional on the boundary. And this is slightly bigger than Sato's hyperfunction. So it means that you consider slightly bigger class of analytic functions on the boundary, and you consider you apply the Poisson integral to this analytic functional. Then you can define the scattering matrix, which assigns to this exponentially growing data to this exponentially decaying data. So you have this incoming and outgoing data, and you can define the S matrix, the generalized matrix, as a map which assigns this. Sorry. Let us return to this one. Yes, which assigns this data from this data to this data. Now, the theorem is as follows. You are given an exponentially growing solution, exponentially growing data, then you can find a unique solution to the Schrödinger equation, which is exponentially growing at this cusp, however, which behaves like the usual physical solution as a regular infinity. And by looking at the behavior of the solution at this cusp, you can consider the exponentially decaying part. And so this is a solution to the Helmholtz equation, which is exponentially growing at the cusp and polynomially bounded at the regular infinity, and contains an exponentially decaying wave at the cusp. And the general S matrix is the mapping which assigns exponentially growing wave to the exponentially decaying wave. Then, the theorem is as follows. Suppose you are given two such manifolds with cusps, and suppose you are given two generalized scattering matrices. And suppose this component, one component, coincide, which means that you send exponentially growing wave from here, and you look at the reflected exponentially decaying wave here. Suppose that this one component of the scattering matrix coincide. Then these two manifolds are isometric, including the structure of these conical singularities. So more precisely, there is a homeomorphism between these two manifolds, and which maps singular points to singular points, and except for this singular point, this map is an hyperbolic isometry from this manifold to this manifold. Okay, sorry, almost 2 minutes. Sorry. And so, for the case of the functional group of the first kind, what we get is as follows. If we have if we have two same scattering matrix, it implies that these two spaces are conformal, and the discrete group are conjugate each other by some element from SL to R. The proof uses a boundary control method, and which essentially means that from the scattering matrix, you reduce the problem to so you introduce some artificial boundary here, and you reduce the problem of determining the manifold from the Dirichlet normal map from here. And we are now currently trying to generalize this result for the three-dimensional or three or more dimensional case. In that case, the important thing is the manifold at infinity is no longer a manifold, it's again an orbifold. However, we can do everything almost the same way. That's all. Thank you very much.
Are there any questions or remarks? This is not the case. Everything is clear.
Maybe
Oh, maybe.
Yeah.
So you need, besides the scattering solutions, you need also some increasing solutions.
Increasing solutions, yes, yes. We need it, yes,
So
yes,
it's
yes.
not a big deal.
Yeah. But if the n is Euclidean, we do not need it. From the standard S matrix, you can define this, you can construct this sort of generalized S matrix.
Okay, if there are no other questions, then I thank you again.